Welcome back. So we're still dealing with first order differential equations and their applications. So let's have another example. So we have another worked examples. So these problems is a sewing machine, a sewing machine. Is it machine or machine? Anyhow you call it is fine. Or machine. A sewing machine is found to depreciate is found to depreciate in value at any given time, value at any given time at a rate proportional to the square of its value, at a rate proportional to the square, at a rate proportional to the square of its value. So that is that. And we're told that Adam bought a sewing machine for 12 naira and found out it's depreciated and it depreciated depreciated in value by 4 naira in 2 years, by 4 naira in 2 years. So we now asked, what will this machine be worth? What will this machine be worth in another 10 years? In another 10 years. All right. So let's have a look at this. This is a kind of problem where you're given just a word problem. You're expected to just interpret it based on what you already understand about rates of change of a variable, okay, with respect to some other variable. So it will happen that your direct interpretation of that, as we've seen in previous examples, will result in a differential equation. Of course, in this case, first order differential equation. So this is an example of such a situation. So you don't always have things that you have seen before or you're already used to. A problem may be formulated for you. It may be a problem that you even observe by yourself and you model that problem and it results in a first order differential equation. So this is one of such cases. So let's see how this works. Now, how are we going to interpret all of this using the concepts we already developed for first order differential equation? Okay, so let's see how this works. I will say solution. So the first part says you have a sewing machine which is found to depreciate in value at any given time. That means it doesn't matter the time difference, any time at all you're observing its rate. The rate of depreciation. It is depreciating at a rate that is proportional to the square of its value. So we can say then that the value is what is depreciating. That means the value is changing. So the variable we have to monitor is the value of this sewing machine. So we can use some letter to represent that variable. Okay, we're already used to y and x. Okay, so in this case we have x and c. So let's say let y be the value of the let y be the value of the sewing machine. Okay, at any time. Okay, at any time t. So we can see that the value depreciation simply means a drop in the value of a property or a material over time. So if y represents the value of the sewing machine, it means that y is some variable that depends on time. So y is in this case the dependent variable and t is the independent variable. So we now go ahead to see what we have here from this statement. We're told that it depreciates in value at a rate proportional to the square of its value. Okay, so that means if we get the value at a given time, which is y, the rate at which that value changes, depreciation simply means a drop in value. So that's a decrease in value. So how do we model that? The rate of change in this value, okay, with respect to time, that is, as time changes, how does this change? That rate of change is modeled by the expression dy dt, that is derivative of y with respect to t. So the fact that it is depreciating means that there will be a drop in the value with respect to time, which means we expect our dy dt to be negative. So if you want to express that, now we'll get back to that, but it says that that rate at which it depreciates is proportional to the square of its value. We know its value is y, so that means this rate of change is proportional to the square of y, that is, it's proportional to y squared, all right? And whenever we have a proportionality relation, we will get rid of it to actually express this mathematically. We'll say this is the y dt equal to, then when we replace this proportionality sign with equal to sign, we introduce a constant, which is called the constant of proportionality. So in this case, you can say your constant is minus k. We usually use k for the constant of proportionality. You can say it is minus k, and you can say it's k, as we have seen before. But we know that the y dt is meant to be negative because y is decreasing with respect to time. That means as time increases, y is decreasing. So we expect the y dt to be negative. So you can have that in mind and say this is equal to minus k y square. That is fine. It means then that your k will be a positive value when you get it. And if you don't mind, you just leave it like that. You just write k, which is what I'm going to do here, k y square. Yes, this can still express the fact that y is decreasing with respect to time. It just means that when you obtain the value of k, it will be a negative constant. Okay, so it makes no difference. So if you put minus k here, maybe the constant eventually evaluates to 5, and you used minus k, that means you get k equal to 5. If you use just k, you get k equal to minus 5. So essentially, it is going to be the same thing. All right. So this is our model that expresses this situation as communicated in the first paragraph. Okay, so we take note of that. This is the differential equation as it is. We can actually solve it. If we solve this differential equation, we will obtain the relationship between y and t. So it will tell us the value of y at a given time t. Okay, so we can do that as it is, and then come back to consider the other parts of the problem. So we can solve this directly, and of course this k is some constant of proportionality. When we solve this, we'll be able to get our y as a function of t. And for us to do that, we ask ourselves, what kind of differential equation is this? Of course, we know it's a first order differential equation. What kind of first order differential equation is it? That will determine the solution method. And we've said that this should be the checklist. Check if it is separable. If it is not separable, check if it is an exact differential equation. If it is not exact, check if it is a homogeneous differential equation. If it is not homogeneous, check if it is a linear differential equation. And if it is none of these, it could be an inexact differential equation that could be made exact. It could be a non-homogeneous equation that could be made homogeneous. It be a non-linear equation that could be made linear. So we check for all of those conditions also. But this is the order of um, simplicity. So this is the simplest to deal with, followed by exact, followed by homogeneous, and so on. So the first thing we check is, are the variables here separable? Yes, we can separate y from t. Y and t are the variables in this expression. K is a constant. Y is our dependent variable. T is our independent variable. So obviously we can separate this. So this is going to give us, when separated, we can have, when we divide both sides by y squared, this is 1 over y squared dy, and this will be equal to, when you cross multiply, this will be k dt. And now, having separated the variable according to what we've done previously, this will be integral of this equals integral of this. So let's have another page here to see how this works. So going further, we now have this to be, what is integral of y squared and 1 over y squared with respect to y? Of course, that is y to power minus 2. So this is basically y to power minus 2 plus 1 divided by minus 2 plus 1. And this is equal to, k is a constant, so we can move it out. That is k multiplying t. So from here, we can simplify this further. Let's move into the new line. This is going to be equal to, so y to power minus 2 plus 1, that's y to power minus 1 divided by, this is minus 2 plus 1, which is minus 1, and this is equal to kt. And of course, we have to include a constant of integration here. Okay, so we use c for that constant of integration. This is constant of proportionality. When we integrate both sides here, we say we have to include one constant. If you included another constant here, it won't make any difference, because that's just this one serves the purpose of both. I discussed that previously. Okay, so from here, we're going to have this to be equal to kt plus c. So when we simplify this further, we see this is just minus 1 over y, if you like. So this is equal to kt plus c. So that is what we have for the relationship between y and t. And if you like, if you try to make this, or decide to make this the subject of the formula, when you multiply through by minus, you're going to have this to be 1 minus, sorry, that will be 1 over y. We'll multiply through by minus, if you like. This is going to be 1 over y equals, that will be minus kt. Okay, you should do expect minus kt minus c, but c is a constant, an arbitrary constant. It's unlike this one. This one is constant of proportionality, which derived from the given differential equation. So we cannot just equate this to anything. But this c is an arbitrary constant. So minus c is also an arbitrary constant if c is an arbitrary constant. So basically, we can just write this as plus c still. Okay, so we're good to go. We know from here that when we take the inverse of this, we're going to have y equals 1 over minus kt plus c. Okay, so that is the relationship between y and t. So now let's go back to the question statement. Before we can evaluate the value of y, which are the value of the machine at any given time t, this will be a relation between y and t. Now it is a relation between y, t, k, and c. So we need to find the values of these constants. We need to find the value of k and also the value of c. And that is why we have been given initial values here. It says Adam bought a sewing machine for 12 naira. So we are now monitoring what happens from the point Adam bought the sewing machine. So that will be our time t equals 0. So our time t equals to 0, then we say the price of the machine was 12 naira. That means when t is equal to 0, y was equal to 12. Okay, so we know that. So given that Adam bought the machine, so that will be our year 0, that is the first time. Okay, at t equals 0. Okay, for y equals 12 naira. So in this case, our y will be equal to 12. Y is the price or the value in naira. Okay, so let's just write y is equal to 12. So that means when y is equal to 12, our t was equal to 0. So we put y equal to 12 here. 12 will be equal to 1 over minus k into 0, then plus c. So minus k into 0, that is 0. So from here, when we cross multiply, and we're going to have our c to be equal to 1 over 12. So it's as easy as that. We know what our c is by doing this. And then look at the next statement here. We're told that Adam found out it's depreciated in value by 4 naira in 2 years. By 4 naira. Please, this is very important. This word is very important. The statement or the implication would have been different if it says it depreciated in value to 4 naira. 2 will mean that the value became 4 naira after 2 years. So in this case, it depreciated by 4 naira means that from the initial value of 12, we remove 4. So that means after 2 years, the value became 8. That's 12 minus 4, okay, which is 8. So given that the machine depreciated by 4 naira, okay, meaning that y will now be equal to 12 minus 4, which is equal to 8 in 2 years. So our t is in the years. So you see, all of the time variables in the question are quoted in the years. So we'll just work with that directly. And so this is in 2 years means when t equal to 2. That is, we're taking our t equal to 0 to be the time that Adam bought it. So t equal to 2 will be 2 years after Adam bought it. So in 2 years. So what is the implication of that? That means when y is equal to 8, our t was equal to 2. So we substitute that in this expression. So we can say this is equation star, for instance. So it was equation star that brought about this. So if we substitute this observation into equation star again, that will give us when y equals 8. So we're going to have there 8 equals 1 over, so we have minus kt, that is minus k into 2, then plus c. So we already found our c to be 1 over 2, so we just put that here. So this will be plus, sorry, 1 over 12 plus 1 over 12. So from here, we'll find out what k is meant to be. So that means from here, when we invert both sides, this is going to be 1 over 8 equals minus 2k, then plus 1 over 12. So basically, we're going to have, when we collect like terms, we're going to have this to be minus 2k equals 1 over 8 minus 1 over 12. So 1 over 8 minus 1 over 12, what does that give us? Then we divide it by minus 2. So we can just use our calculator to do that. So that's 1 over 8, 1 divided by 8, then minus 1 divided by 12. So that's our answer. Then divided by minus 2. So that is minus 1 over 48. So that means then, therefore, our k equals minus 1 over 48. Okay, so now we have the two constants. That is what this the information supplied here has enabled us to get. So we now get from using the two constants that we have now obtained, we can get y strictly in terms of t. So we now use that to evaluate the value of the machine at any point in time. So we want to get a value in 10 years, in 20 years, in 30 years after the purchase period, please. So if we purchased it this year and then we want to get it 20 years after purchase, we know we're just substituting t equal to 20 into that expression. So let's have another page here first. So from all of these results, when we substitute all of this into equation star up there, that gives us, in substituting into equation star, we'll have y equals, so therefore y will be equal to 1 over minus k. As expected, we've gotten k to be negative now, which is what I told you when we started, that I am taking k to be this. If you wrote minus k here, it's fine. You would get the same expression, just that your k now would have been positive. And anyway, your final expression would have been the same. Okay, so what we had here was minus kt. So we have now obtained k to be minus 1 over 48. So this is going to be 1 minus of minus 1 over 48. That's 1 over 48 multiplied by t. So that is kt minus kt. K is minus 40 or minus 1 over 48. So negative of that, that's 1 over 48t plus c. We've obtained c earlier to be 1 over 12. So this is going to be um, plus 1 over 12. So this is plus 1 over 12. So this is the expression that helps us to evaluate what y is at any time t. So if you want to get what y is at time t equals 0, we substitute 0 here, it should give you 12, which was what the machine was bought for. Okay, and if you substitute let's say 2 here, we're told that the value dropped by 4, which means it became 8 in 2 years. You substitute 2 here, it must give you 8. If it doesn't, then that means there's an issue with these calculations. Okay, so we can easily check that with calculator just to be 100% certain that we've done the right thing. So from here we see that y is equal to this. So let's enter this as a formula in our calculator. Of course, you can simplify this and bring all of this to the numerator. It's fine if you do that, but we don't have to do that here. Okay, so I don't want to do that. So this is 1 divided by 1 over 48. So this is 1 divided by 48 multiplied by t. So let me use x instead for our variable here, and plus 1 over 12, so let's put 1 divided by 12. Okay, so that's the expression. So we can calculate this for time t equals to 0. That's when x equals to 0, it is 12, as you can see. When x was equal to 2, and so this should be give us 8. So it means that after 2 years, as given here, the price became 8. Okay, which was the interpretation we gave this all along. All right, so quickly, you should understand what we've done here. What we've done here is that we have gotten here a relationship that applies to Adam's machine specifically. This is an expression that tells us the price of Adam's machine as in years from the point of purchase. Okay, so and this expression up here is the model or the relationship that applies to any kind of machine, and indeed any device really, whose rate of depreciation or the rate of change of its value varies, with the square of its value at any point. So that's it. That was the only thing we considered to come about this equation. So depending on the specifics of that machine or that device or whatever object you are dealing with, then you will have different values of k and expectedly different values of c, as the case may be. All right. So it is the specifics of this problem, which is in this case having to do with Adam's machine, that actually brought about the values of these constants. So if it were some other machine, you may have to evaluate these constants differently. Okay, but now we're still dealing with Adam's machine, so we're good to go. We already know what the actual expression should be for the price, strictly in terms of the time. So the question now says, what will this machine be worth in another 10 years? Another 10 years. So the use of another here tells us that the another will be 10 years after these first 2 years. That is, it has depreciated by 4 naira after the first 2 years, at the end of the first 2 years. Then in another 10 years. So what will the value be? That is, what will the machine be worth in another 10 years? And for us to get that, we know that T in our expression, as we've said, is from the point of purchase. So if 2 years after purchase it has already depreciated by 4. Then if we want to get what the value will be in another 10 years, that means we should be looking at 12 years from the point of purchase. So in another 10 years, we'll have 10 plus the previous 2, that is 12. So we'll have 12 years from the point of purchase. If the word another was not there, then it might become it might be that we just take this as 10 years and work with it directly. But in this case, it's in another 10 years. That is after these first 2 years, when we see another 10 years, what will the machine be worth at that time? So we want to find y. So, so we just take note of that. So in another 10 years, in another 10 years, our time t will be equal to 2 plus 10, which is equal to 12. And so that the value of the machine y will be equal to 1 over 48 multiplied by the time, which is 12, plus 1 over 12. So we'll just evaluate this. This is 1 over 4 plus 1 over 12, and you can put that in the calculator. And let's just use the calculator to see. Let's calculate what happens when x is equal to 12. So 12 years. So this is going to be equal to 3. So therefore, we're going to have another 12 years. This will be equal to 3. Okay. So we now interpret our result based on the context of the problem. That means the value of the machine will be 3 naira in another 10 years. So we now say that hence the machine will be worth the machine will be worth 3 naira in another 10 years. All right, so that is that about that. So 3 naira, that is the final answer. So that is how to deal with problems of this kind. Again, just interpret the problem, take note of the rate, what is proportional to, or how the rate varies with respect to any variable it depends on, or with respect to itself for anything you are given. Once you interpret that correctly, you get a differential equation. Solve the, of course, in this case, expectedly, first order differential equation using the concepts we've developed so far. I mean, the solution methods we've discussed so far. And once you have that, you're good to go. You're going to have a lot of constants. Take note of the one that can, yeah, you can play around with. Your constant of integration can be made to be anything you want it to be. Multiplying through here by -1, we saw that this was just going to give us c. Okay, instead of it being minus c, we wrote it as c. That is excusable for a constant of integration. It will not be excusable for this constant because this is constant of proportionality that actually tells us the behavior of this equation. So we expect this to be negative. Looking at the fact of this problem having to do with depreciation, which means a drop, implying that the y dt should be negative. So that is why we cannot just make this whatever we want it to be. Okay, so that is the end of this lesson. We proceed uh, from here in the next chapter to begin to consider second order differential equations. Thank you.